Hi everyone, I'm Yaron Chaviv. I'm CTO and co-founder for IGUAZ, which is a data science platform company. And I'm going to speak to you today about how to accelerate data science productivity and how to accelerate data science to production using MLOps best practices. We're going to cover the key best practices on how to help you achieve faster productization of your machine learning efforts. So let's first start and talk about the key challenges in operationalizing machine learning. So we have few things I put here on a slide, which is one is the siloed work. We have different teams in data science, data engineering, DevOps, ML engineers, and so on. And usually they work with different tool sets. One is working with Jupyter, the other one is working with containers, one is working with Spark, and so on. So this is part of the challenge, and we need to try and get some collaboration around here. The second key challenge is the long process for taking something that you built in research and productizing it. There are so many steps that we're going to cover in that long journey and trying to figure out how to shorten that process. We have another key challenge is where we work on training our model and build our model. We work on data sets that were extracted manually, whether it's directories of files and images, whether it's data sets and tables and compressed CSV files or Parquet. Those were extracted manually, but when we need to serve the models in real applications, we need live integration with different data that's coming from live sources, databases, video streams, logs, and so on, chats, interactive sessions, and we need to figure out how to prepare those features into and serve them into our model in the production pipeline. And final challenge is really about maintaining the accuracy of your model. You train your model, everything looks good, but in production, the model accuracy starts decaying and starts drifting. So you need to figure out different ways of monitoring your model as well as fix the challenges when your model is losing accuracy. We're going to speak about some of those challenges, and I'm going to try and do it using a few tips, six tips that will help you turn your MLOps effort into something that leads to production, into real business values. So let's start with the first challenge. The first challenge is the fact that it takes so long to take something into production, into something that really works in online, in real business application. And the key tip here is to adopt automation. Automation meaning having managed services, having the notion of serverless. So you can take your code or your piece of work and productize it in a relatively fast and resource non-intensive way. And the way to do it is first we need to understand that when we're developing something in research, it's not really led to production. In many cases, we re-engineer everything we do. So we take our notebook and we play around with it, we create models, etc. But in production pipelines, we have to integrate with live data that arrives from real sources. We need to be able to train and prepare the data at scale, and we need to also serve the models in an online fashion, also in a scalable way, work with real data that comes from streams and other inputs. We need to model our models. We need to retrain and redeploy our models. We need to change different things in our entire pipeline. We need to load it back into production systems. So that requires a set of disciplines that are not maintained in the research. There's a lot more work in driving workloads that have been developed in research to redeploy them as production pipelines. And in many cases, it's done from scratch using other technologies. And why is that? It's because there's so many things, as you can see here in the diagram. So we built something. We have some code running as prototype on our notebook, but then look at how many steps we need to go in order to turn it into production. We need to take that code. We need to package it in containers with all sorts of dependencies. Then, usually in production, we may need to address different level of scale. So we need to be able to partition our workloads, whether it's load balancing, the traffic coming in, whether if it's a large data set, we need to partition that data to smaller sets to work with. We need to potentially distribute the model training work, or maybe apply AutoML and distribute the work of AutoML across different algorithms and different model permutations. Then finally we scaled it out good, but what about performance in production? We may need to serve a certain number of requests per second, or we need to be able to work within some latency constraints, or we don't want to waste so many energy on this, and we may have different and more efficient ways to write and implement our code that it will address much higher performance. For example, using GPUs or applying caching or parallelism at your work, tuning your queries on the data, and so on. So this is another set of work items that are usually not done by the data scientists. They're done by data engineers, DevOps, and so on. Now we've gotten the performance right, but what about instrumentation? We need to monitor, we need to log, we need to version everything that we do. We need to guarantee security for everything, for data access, for API access, and so on. And finally, we want to automate the entire process. So we need to apply CI/CDs and workflows and canary deployments and rolling upgrades and so on. So this work is really the longest stick. This is really the most amount of work. It's not about developing the model, it's about doing all those different things and driving that model to production. So we want to apply automation to all those different steps so we can shrink this real effort from having many people working on it for months to essentially a matter of weeks with less people working on those set of tools. And this is really where managed services or serverless automation comes into the play. Now, we've developed an open source system or open source framework called MLRun, which is really about trying to automate the machine learning or machine learning operationalization effort. And the way that it works is that you work with your IDE, whether it's PyCharm or VS Code or even a notebook. And from the notebook, you can start working already. Now, you may not work at scale, but you still want to instrument and monitor all the activities that you're doing on your notebook. At a certain point, you may need a bigger set of resources, or maybe GPUs, or you want to do things at scale, and so on, or you may want to access the cloud. So this is really where you automatically translate your code from the IDE or the notebook into a microservice using a single command. And that runs on a cluster which potentially have GPUs and CPUs and much larger scale. Now, after you develop something, whether it's a training of a model or evaluation of your model or a serving function or data manipulation preparation function, you may want to build a pipeline. Pipeline is like a multi-stage pipeline where, for example, you take in data, you run training, you run testing, you produce a model, and so on. And in some cases, those pipelines could even be more complicated. Once you have this pipeline working, you have to essentially go and monitor everything that happens there, the activities, the performance, the results, and so on. So essentially, you have a full workflow for starting with development, automatically translating your code into microservices, stitching a bunch of microservices into a pipeline using some backend engines like Kubeflow or Nucleo serving, and then finally monitor. In many cases, we repeat using the same features or the same functions or the same models. So this is where we want to have a repository for storing those features or those models or those pre-baked functions, and then just applying them at our new pipelines. This accelerates the work quite extensively because you're reusing the work items that we have done, whether those are features or functions or models. And then as we build those pipelines, essentially we have three different layers. We have the first layer, which is storing the data or the models. That's called a feature store or a model store. And then we have those microservice functions that apply each one of the steps in our pipeline, whether it's ingestion or data preparation or model training or model validation or deployment. In the deployment, we also have a set of different things we need to do, the serving functions, the monitoring functions, data preparation and ingestion functions, and so on. And finally, some orchestration on top of all of that. One of the things that we developed is a set of serverless engines for different workloads. We have Nucleo for real-time, we have a Spark serverless engine for analytics jobs, or Horvath serverless engine for deep learning. This is all part of this MLRun open source project. And the idea is that usually serverless functions are slow, they're stateless. But here in machine learning and data science, you need statefulness and you need performance and scale. So what we've done is essentially build serverless engines that are designed for data science. They have the performance, they have the scale, they have the concurrency built in. So you can essentially go and take your code from your notebook or IDE in a single command or API call. You translate it into a fully working microservice on Kubernetes with data, with monitoring, with security, with everything. Now, it's not slowing you down, and that's really the nice thing about it. It's essentially accelerating your performance. So you can take the same code that you've written and run it about 20 times faster when you put it in a parallel high-performance serverless engine. There is a nice blog that we've done together with NVIDIA on that, towards data science, showing this use case that you can essentially take something that worked with like 20 megabytes per second, run it at like 500 or 600 megabytes per second using those serverless engines and some NVIDIA capabilities. Now, as we build those functions, the nice thing about a function, it's self-explanatory, it's serializable, you can actually go and save it and later on use it in a different pipeline. And another key thing about scaling is that the scaling is built into the serverless engines. It essentially works again with 3 different layers. You have the microservices, there's a high-speed messaging layer that could leverage NVIDIA RDMA technology for shuffling data across those microservices. And there's also a high-speed data store that stores the intermediate results, the data, the files, the code, and shares it across the different containers. So you can essentially build very large-scale workloads on that system without writing a single line of code, just scaling out your code transparently. And that's pretty cool. This is an example of essentially doing a full real-time pipeline using the serverless technology. It's using the Nucleo real-time engine at the back end, but there's a lot of abstraction on top of it. So let's assume we need to build a real-time pipeline which gets some data, enriches it with some data sets, does some pre-processing on the data, builds a model ensemble, which is essentially taking different models from different algorithms or different data sets and creating a combined result, which leads to much better accuracy, and then sort of post-processing after we've done that. So we build that. We can build and design that pipeline using some Python code. You can see an example of the code. There's the full notebook is part of the MLRun documentation. You can go and see that. And here in like a dozen lines of code, I described the full real-time pipeline. In order to test that pipeline, I have a few lines of code, creating a simulator in my notebook or my IDE, running some test data against it, seeing that my real-time pipeline behaves as it should. And in order to deploy that into a real-time, high-performance, auto-scaling cluster deployment, there's a single line of code that I need to do, or a single command line, which is just deploy. This deploy command essentially takes that code, translates it into microservice, chain those services together in a pipeline, and monitors this entire thing. And this is done using a single command. So now that we've solved the long time to deployment, let's tackle the second challenge, which is the inefficiency due to effort duplication and siloed work. We talked about the fact that we have different teams. We have data scientists that work with their notebooks. We have data engineers that work on their Hadoop or Spark. We have DevOps guys working on their Kubernetes. And now we need to think about how to consolidate all of that work into one place where we don't have different practices, different tools, and people work in collaboration. So the challenge is that you have different silos. You have first the deployment arena. You have the research environment where you take data, place it in a data lake, then you do some transformations, or you place it in some storage, a file system or something like that, and then you run training. So that's just the research pipeline. Now, as you go into production, you have a deployment. This deployment have to attach to real-world data, which is like streaming data, log files, operational databases, video cameras, and so on. So all that data needs to transform dynamically using some real-time pipelines or some, containerized workloads and all of that. The results of that are stored in some online databases or real-time file systems and used for the model serving. Now, as we serve the model, we didn't finish here. We also have the monitoring aspect. Everything we served has to be logged, and this log is used to help us determine the accuracy of our model, if we had any drift, if we violated any sort of legal policies, or if we want to explain our models and so on. So we have to monitor and analyze all the return data from our model serving and do further analysis. So we have different arenas where we deploy our technology. And also this is siloed by different groups. We have the data engineers that usually treat the data ingestion and preparation. And then we have the data scientists that work off like Jupyter notebooks and so on and develop models for training or serving part of the models. And we have the ML engineers, which take that piece of code in the notebook and re-engineer that into some containers and Kubernetes and all of that. And this is quite challenging because we've essentially duplicated the stack for 3 different locations, 3 different areas of deployment, and 3 different disciplines that use different tools. And that has many challenges. Also, it impacts our accuracy because if we do different implementations of that pipeline, obviously we're not going to get the same results. And again, a lot of extra efforts are being applied. So the right way to do it is to essentially have one platform, which is trying to automate everything. So it has one store, a feature store, and we're going to speak about what is a feature store and how it's used in a minute. This is really where we place all the data. We catalog, we register, we process all the data. And then we have different services around it for training, for serving, for testing, for monitoring, for analysis, and so on. And this is used by the same set of people. We don't separate it by different teams and give them different tools. You want to run analytics job, use it on the same platform. And now the data scientists want to build some features. He can do it by himself. It doesn't necessarily need the data engineer to do simple features or things that are more statistically oriented. And the MLOps engineer doesn't need to re-engineer the code. He can essentially just go and deploy something that is already stored in the system without re-engineering all that effort. So this is, once we've addressed that silos, there's another challenge, which is, okay, now we have silos of infrastructure, not just silos of work. Each one has his sort of mini cluster. People have their workstations and so on. Or people just go to the cloud and rent some virtual machines, and then you find out at the end of the month that it costs you quite a bit. So instead, why not just pool all those resources together into an elastic cluster that can dynamically shrink or grow, and have people just go and schedule the work items on that cluster, essentially sharing the pool of resources. So in total, you need actually less resources, and you keep people more happy because you can allocate more resources at a time for individual data scientists. So this is what we really did in IGUAZ in our platform. Is you can just take a bunch of servers or virtual machines. It's also certified on DGX. It's a DGX ready software stack. And you take all that software, you run Kubernetes on top of that cluster. We can bring the Kubernetes with us, or sometimes you bring the Kubernetes. You have a common data layer. This is really where we shuffle all the data. We move data around between those microservices. We scale out the access to the data and all that using that fast data layer that can provide different data services like file and object and key value and so on. And then you just schedule workloads on top of that shared cluster. And you can schedule workloads that will live on a single system, or they can scale out across multiple servers, so you can gain much better scale and performance. And you have all the suite of tools around it for creating the production pipelines, services for the different aspects, machine learning, deep learning, and so on. Development environments like managed notebooks and integration with IDEs. And you also have all the monitoring aspects of tracking everything that you do, experiments, resources, infrastructure, features, data, and so on. So this way you can accelerate the time to production, but also consume a lot less resources because you share and pool the resources, and keep everyone happy, because you know at the time someone can grab a much bigger set of resources for his job, and this job will run much faster. Now, part of the nice things about it, it's fully managed set of GPU and CPU resources, and this is a nice snapshot from the tools. Some of them are open source, like the Nucleo screens here and MLRun, or most of them are open source. And you can see that when you're launching a job or a service, you can actually specify the amount of CPU and GPU resource you want to use. And then this is also gets tracked with your workload. When you run the job, you can see what were the resources used for that job, and you can track the behavior and all that. And you can also track it in real time. You can see in real time how much CPU or memory is being consumed by every work item, every service, every workload, every job. You could even create billing around it. This guy is using GPUs too much, maybe, and you want to provide some higher bill for that. From the infrastructure perspective, the IT folks or the DevOps guys can just look at the total amount of CPU or GPU usage, and this way decide maybe they need more resources, or maybe they can decommission resources and place them in a different cluster. So again, having that fully automated orchestration coupled with nice monitoring of all the resources is very, very powerful. Now, again, you don't need a full GPU to run the workloads today with the new technology from NVIDIA with A100 and the May multi-instance GPU technology. So the nice thing about it, you can actually take a single GPU card and slice it up to 7 different pieces of different sizes. And now the same GPU can run 7 different services concurrently. Not everyone needs a full GPU. Sometimes you can run a workload on half a GPU or quarter of a GPU and so on. So this is just an example of how you can use MIG, essentially go and partition the GPU to different sort of instances, and then have different applications run on top of those different instances. And this is also supported on Kubernetes, etc. Now, as we build the software stack, now let's think about how to scale the hardware. So the nice thing about it is that this entire stack can run on a standalone DGX station with A100 technology. And as you grow, you may want to cluster it, so you can actually take multiple DGX systems or even add some other servers and interconnect them using the NVIDIA sort of switching technology, Mellanox base with high-speed networking to linearly scale your cluster. And as you grow, you may even grow further and you add more GPUs and more DGX systems and servers, but also add external storage like NetApp filers or Pure Storage or other storage technologies, object store, and so on, to build a very large pool. And so even if you're a large enterprise and you have lots of data scientists and engineers working on the system, you can create a pool of resources and manage them pretty much like a cloud. So moving to the next challenge. So, okay, the key thing in data science is data. Data is the thing that is what we mostly deal with. Today, machine learning is quite automated. You have AutoML, so it selects algorithms for you and even parameters for you automatically based on a bunch of experiments and some other knowledge. But the thing that you always keep on doing is preparing data and storing data and using data and ingesting data, etc. That's really application specific. So the point is that there are things to do it today in, and we're going to speak about it, in the cloud providers have something called a feature store and internally. And this is something that people can now use because it's becoming more and more prevalent. And there's also open source tools like ours and commercial tools and so on. So what is really feature engineering and what is a feature store? So when we build training or serving and so on, we cannot just take raw data. We need to take the raw data. We need to apply some analytics or data engineering on that raw data and turn it into something more meaningful. Like, we get lots of log data, but we need to process it and see, okay, the customer purchased X amount of products in the last hour. This is a feature. This guy usually has more activity in 7 a.m. in the morning, or even on audio files or or text files. We may want to apply NLP, so we take paragraphs and we break them and we do sentiments analysis or entity extraction and so on. Or even in video, we may rotate the pictures and so on. So we need to take the raw data and transform it using different transformation functions into something meaningful that feeds our machine learning workloads. And we need to do exactly the same thing in 3 different applications. We need to do it for training on offline data. We need to do the same now in the production pipeline, get data from real sources, streams, logs, etc., build our feature vectors and use it in the serving pipeline. And we also need to do it for governance because we get all the data and we want to be able later on to measure our accuracy, be able to explain why a certain model behaves in a certain way. So we also need the features are the key thing in that governance. So data engineering and features are the things that really drive our machine learning and AI activities. And so in order to simplify the work, all the sort of big service providers, Netflix and Uber and Twitter and Spotify and everyone, they built something called a feature store, which is a central place where you can build a pipeline for creating those features and with the transformations, catalog those features, and then someone else can just go and grab, I need those features and those other features in order to train my model on. And then as you go into production, the feature store would automatically create the real-time features for you as well without extra work. So this is a very significant way to simplify and accelerate the way that you're driving your production workload. So in IGUAZ, we also added a feature store into our MLRun project, which is open source. And it also integrates with different data sources, including the IGUAZ high-speed data processing engines. And it has several aspects to it. So first is you build transformation pipelines. Transformation pipeline is essentially taking some data from some source. Source could be a file, could be an HTTP endpoint, a stream, and so on. You conduct a bunch of transformations on that in order to turn it into something more meaningful that's used in machine learning, aggregate and what are the encoding and imputing and so on. And then store it and catalog in different places, some real-time storage like a key value or a high-speed database, and some offline storage, maybe a file like a Parquet or a CSV file. And you store it and catalog it in a way that all the information about the features, the statistical behaviors of the features, you can label the features and so on. Now that we cataloged all the features, we want to build some new model. We go to the catalog, feature store catalog, and we say, give me those features. Let's create a feature vector. Instead of doing a lot of work on my notebook and on data engineering, just going to the catalog, sort of an a la carte machine learning, build those features and drive them into training with 2 commands. You can see here the 2 commands on the screen. Get offline features, turn it into a data frame, run your scikit-learn or TensorFlow. That's it. So think how much work we saved in that process. But even more work is saved when you're transferring that into production. So as you move into production, this will automatically build a real-time pipeline for you to generate those features in production. And in the model serving layer, you only use 2 other commands, to get the real-time feature vector. And every time you get a scoring event, a prediction event, you just feed in the indexes or the keys, and you get the full feature vector, and you use that feature vector in your pipeline without any additional data engineering work. That's really awesome, and that will drive your production much faster. And also the monitoring, we're going to speak about it in a minute, is integrated seamlessly into that process. The monitoring pipeline will feed from the same type of features and their metadata. So moving to challenge number 4, models may be inaccurate, and we need to have visibility into that. And why they're inaccurate? Because they may lose accuracy over time, because things change. So what we need to do is make sure that the model is being monitored, and once we identify challenges with the model like drift or accuracy problems and so on, we may want to apply something to correct that problem. Retraining, ensembles, changing weights, all those different things. And we want to build that into our machine learning pipelines, not as a separate paradigm. So first, what does it mean to have a problem with our models or accuracy or drift problem? So let's assume that we train the model on a set of behaviors. Let's take COVID as an example. So people may buy certain things usually, but then as things change, for example, now in COVID, you stay more at home, so you buy more food because you don't go to a restaurant. You may buy other stuff and so on, or even your flying habits change. You used to fly once a month, and now you're not flying, like me, for example. So when our behavior change and we train the model on certain behavior now, it means that the model will not behave as expected. It will produce different results than what we've trained our model on. So that means that we're going to lose the accuracy. Now, there are different types of drift, and some of it may be because of seasonal data changes. In the summer, people wear shorts, and in the winter they go and buy long sleeve and coats. Okay, so that's a seasonal change. That may be something which is incremental. Over time, things go and change, or things could be sudden. A plane crash, something happened. All the world is talking about it and tweeting about it. So those different changes need to be monitored. But we also need to understand that we have different type of changes. We have changes on the X factor, on the inputs. The data pattern change. The age is different, the amount of stuff people buy is different, etc. And that also leads to an inaccuracy, because if the data pattern change, in many cases, the result, because it was trained on a different data, will also going to be change. And we know how to. It's rather simple to track the data changes, because you apply statistical methodology. You check the average of a different feature, a certain feature, and you can see that the average change, that probably means that the feature is misbehaving. There's also monitoring the accuracy or the Y value. We've predicted that certain thing was going to happen in our training, and now in production we actually see that it misbehaves. It produces different results. Because after some time, for example, we show someone an ad, and after a few minutes, we know if it clicked or didn't click. So we can measure the accuracy of the user activities after some delay. So we can take that delayed data and compare it with the real result, and we can see what was the accuracy difference. So we have all those ways to monitor our models, and now we just need to apply it into a more automated pipeline. So what does it mean to build a concept-aware or drift-aware system? So we usually take data, we apply some learning on it, and we do some prediction on it. Good. But now we also need to think about the feedback loop. So we need to also measure the differences between our predicted results and our actual results. And this way, we can essentially trigger an alert. And then we will apply something to that alert, maybe retraining our model, maybe notifying someone, or maybe just switching the model from a summer model to a winter model, or a model that works in a different way according to a new situation. Okay, so this is essentially, we have to apply this feedback loop into our system. And the way that it works within MLRun and the Nucleo system and the IGUAZ platform is essentially you have those model serving frameworks that that gets those requests and generate the predictions. We talked a minute ago about feature store, so they get the actual features enrichment from the feature store. But the model serving functions also track everything that happens. They track the performance, they track the incoming values, they track the prediction, and so on. And turn everything into a stream, a real-time stream. Then you have other set of functions that listen on that stream, and they grab the statistical information about the features from the feature store. They compare it with the real-time feature behavior, both the X and the Y factors. They can also get some labeled data from external sources of delayed data with some new results that can be used to measure the accuracy. And this is analyzing all this set of data using some statistical analysis and so on. And if it sees some misbehavior, some accuracy problems, it will trigger an alert. And that alert can trigger some other microservice function that will do retraining, or can send an email or alert and so on. All this information is also tracked in different systems. It is tracked in a time series and in other databases. So you can actually see that information in Grafana or in the built-in MLRun dashboard UI. Just as an example, this is a screen in MLRun, which again is open source, but also fully managed on the IGUAZ platform. That shows the different models and the different deployments for every model, and the performance, the statistic, the drift, the errors, and so on for every model. This is all based on the analysis that we've done on the incoming and outgoing data from the model. If you zoom in, you have a lot more detailed data about the features, the statistical, the variance of every feature, and so on. So we talked about all that technology, but there's lots of technologies. There's lots of different open source tools that are used. There's commercial tools, cloud services, and so on. So how do you deal with the fact that you have so many technologies here and you need to integrate all of them? So the right approach is to use open source, because this is really where you can go to Slack or Google and search for something and you get the answer immediately. You search the internet, you find examples. This is really, you don't necessarily want to use some technology that would lock you in. But using all those different open source technologies together and managing all of those and configuring them, it's quite a big challenge. So you want to use an open source, but in a managed fashion. So just as an example, look at how many tools you may need to use in a single machine learning or AI stack. And all of those tools require, security and authentication and logging and monitoring, configuration management, mechanism to upgrade and control versions and so on. So it's a huge challenge for your IT and DevOps and even the developers that need to learn how to use all those different tools. It's quite frustrating and quite challenging. So what you really want is someone or some tools that will pack all of that for you in a more shrink-wrapped environment where you can use it without necessarily managing and administrating each package individually. And this is really what we've done at IGUAZ. We've essentially built a stack that on one hand has the lower layer is all the data handling, feature store, integration with different storage technologies, with NFS or object store or databases. So having also the IGUAZ high-speed data processing engines built into that layer. The mid layer is the services layer. This is really where we take all those open source tools, we wrap them under some operator, some automation, and we turn them into a managed service that you can just go through an API call and launch a Spark cluster or run a deep learning job. You can schedule something for later on and so on. So this is the auto-scaling, fully managed set of serverless and services and functions for the different steps in your pipeline. And on top of it, you have another set of orchestration and management tools to make your life much simpler. So all the experiment tracking and model management and job scheduling and building graphs of pipelines for real-time or batch, data governance, data monitoring, billing, and so on. So we've created a full stack where the essence of it is using open source tools, many tools that we've contributed to the open environment, like Nucleo and MLRun, but also the best of breed. And you have machine learning tools, you have DevOps tools, MLOps tools like Kubeflow, you have Grafana dashboard, fully managed, Jupyter, and so on. So this is really about making you focus on your application and your business. So if you look into the way that we're articulating it is you can just go and collect data. You can do the preparation at scale using all those technology we just discussed. You can accelerate the training. You could build the models and deploy them very quickly, and you could fully monitor and manage those models once they're in production, all that by focusing on your main line of business and focusing on the applications. So you can listen more on our technology and other technologies. We have a bi-weekly or Every 3 weeks we have a new webinar. We have the best guests in this MLOps community from different companies like NVIDIA and Microsoft and GitHub and so on. And we talk about different things. So come and learn. You can just go and search MLOps Live. There's also a Slack channel for MLOps Live, and we're organizing different conferences. I'm also writing a bunch of blogs. You'll find me towards data science and other places. And feel free to reach out to me in LinkedIn or Twitter or any other media. I can try and help you with your own challenges. Just feel free to drop a question, not necessarily just on our technology, anything in the MLOps space. So thanks for listening to this session. And if you have any questions, we'd love to answer them in the Q&A session or later on a chat or something. Thanks.